Hello everyone, my name is Cindy Amanyure and I'm going to talk about our project. Me and my colleague are going to talk about reinforced contrastive and non-contrastive knowledge distillation for mental stress EEG signal processing. And under this discussion, we have keywords like mental stress, EEG signal processing, knowledge distillation, reinforcement learning, contrastive learning, and non-contrastive learning. So when we go to the to the next slide, we have the contents for our presentation. So we have the introduction, we have the related work, we have problem statement, we have search questions and objectives, we have research contributions, methodologies, dataset description, the results, conclusions, anticipated limitations, and counter action plan, then references, then the acknowledgements. So, we've been talking about mental stress. Mental stress affects the well-being and daily functioning of a human being, whereby it might disrupt your thinking and also maybe lead to further complications. So we have acute, we have episodic, acute, and post-traumatic stress. This might also become a disorder with time. So we have chronic stress, and this can lead to cardiovascular diseases and mental health disorders. So that's why we came up with this, whereby we're going to use EEG signals for stress detection. We're going to use the non-invasive method to record brain activity, and this is useful for real-time stress classification. So the machine learning techniques applied is knowledge distillation, whereby the machine learning technique, this is a machine learning technique whereby the smaller, simpler model, or we can call it the student model, is trained to mimic the behavior of a larger model, which is also called the teacher model. And the goal is transfer knowledge and insights learned by the teacher model to the student model while reducing the computational cost and memory requirements. Then we also have where sparse learning, where we're going to focus on important features for simplicity. And this refers to a subfield of machine learning that focuses on developing algorithms and techniques that can learn effective models from data while using minimal resources. Then we also have contrastive learning, and this enhances differentiation between stress states. And this is a machine learning technique that involves training models to differentiate between similar and dissimilar samples. Yeah. Then also non-contrastive learning, which is also known as self-supervised learning. And this one does not rely on contrasting similar and dissimilar samples. And instead, it focuses on predicting the input data itself, or it can also predict that a transformation of the input data. Then we have reinforcement learning, and this one involves training agents to take actions in an environment to maximize the reward signal. And the goal is to learn a policy that maps the states to actions, and this helps to achieve a desired outcome. Then we have ethical considerations, where we're going to ensure data privacy, consent, and responsible neurotechnology use. So this is our overview. And this, as we told you, EEG with machine learning enables real-time non-invasive stress detections. So the challenges and research gaps that we found out was limited work on reinforcement, contrastive and non-contrastive learning, Then also real-time deployment challenges due to computational constraints. And we also noticed that there was a need for standardized EEG processing and feature extraction. Yeah. Then also ethical concerns like data privacy, fairness, and AI bias. And then the proposed solution was for us to come up with a unified EEG stress detection framework that combines multiple ML techniques for better accuracy, efficiency, and real-time applicability. So, looking at the domain application problem, the limitation of current methods were whereby surveys and reports are subjective and unreliable. Then there was also a need for EEG-based measurements, whereby EEG signals provide an objective way to measure stress by analyzing brain activity. Then the computational problem were the complexity of EEG analysis, whereby it requires advanced machine learning for accurate interpretation. Yeah. Then also we found a challenge in classification, whereby we have to design a model that can reliably categorize EEG signals into stress and non-stress states with high precision. Yeah. So these are some of the research questions and objectives, whereby, and one of them is how can EEG signals be effectively utilized for real-time and non-invasive mental stress detection? Then also, which machine learning techniques yield the most accurate and interpretable stress classification models? And also, how can the developed models be optimized for computational efficiency, scalability, and real-time deployment on wearable devices? And one of our objectives are to develop an EEG-based stress detection model using advanced machine learning techniques for accurate classification of stress and non-stress states, and also to implement and compare multiple learning approaches, including supervised learning, knowledge distillation, sparse learning, reinforcement learning, contrastive learning, and non-contrastive learning. And these, I talked about them in one of my previous slides. Then also to optimize the model for real-time application, ensuring computational efficiency, scalability, and suitability for wearable devices. Then also to address ethical and legal concerns related to EEG, data privacy, participant consent, and fairness in AI-based stress detection. So this is the methodology we came up with. So we start with acquiring data, EEG data, and then it is turned into non-invasive scalp electrodes. Then it's processed by band pass filtering, and it's also denoised using deep learning. Yeah. Then the features we're going to use are extracted, of which we're going to use time domain features, frequency domain features, nonlinear features, functional connectivity features, where we're going to use graph-based analysis. Then the stress states are classified using supervised learning, contrastive learning, and sparse learning, like to tell whether, yeah. Well, then we go to adaptability and efficiency enhancement. Yeah. Then we use this learning, reinforcement learning, and knowledge distillation. Then we deploy the model into either a wearable device or a mobile application So continuing to the research contributions. So we developed an optimized EEG-based stress detection model that leverages machine learning techniques such as supervised learning, reinforcement learning, contrastive learning, non-contrastive learning, and knowledge distillation to improve classification accuracy. And we're also able to build a computationally efficient framework for EEG signal processing and feature extraction, enabling real-time stress detection on wearable devices. Then we also deployed a novel machine learning strategy that can integrate contrastive learning and reinforcement learning to enhance model interpretability and robustness. Then we also established ethical and regulatory guidelines for EEG-based AI models, addressing concerns related to data privacy, participant consent, and bias in the stress detection signals. So I'm going to invite my colleague to carry on from where I've stopped. Thank you so much for listening.
Good afternoon. I'm going to take you through the research contributions. My name is Kahunde Audrey. Yeah. So we developed an optimized EEG-based stress detection model that uses machine learning techniques like supervised learning. Here, it uses a well-labeled data set for training of the model, reinforcement learning, contrastive learning. So contrastive learning uses both positive and negative pairs, but it maximizes more on the positive pairs than the negative pairs. So the positive pairs are those similar looking objects, similar looking representations of data, while the dissimilar ones are those that are not alike. While non-contrastive learning is the opposite of contrastive learning. Yes, it uses representations of data, but it doesn't rely on the positive pairs and the negative pairs. And we have knowledge distillation, whereby the student model is able to be trained by the teacher model, which improves classification accuracy. Then next, we built a framework for EEG processing. This is seen in the knowledge distillation model, where we built a framework for the teacher model and for the student model. Yeah, this improves signal processing and feature extraction. It helps to minimize the errors since you've broken it down. Yeah, and it enables real-time stress detection on wearable devices. Then we also deployed novel machine learning strategies that integrate contrastive learning, reinforcement learning to enhance model interpretability and robustness. So taking you on to your next slide. We have the output of the EDA code. Okay, the box plot basically shows the distribution of the data, and on the y-axis we have the amplitude in microvolts and the different channels on the x-axis. So this shows that different distribution of data in the data set, specifically in that file, the first file. Then we have the raw EEG signals. These consist of outliers. These are the outliers. Outliers are like the information that's not really necessary when determining the stress detection. Then we have the PCA, which is the principal component analysis graph. And here we were able to analyze two components, a component one and a component two. So component one could be something like maybe stress state, and component two could be the non-stressed state. So yeah, it just helps us to analyze those two states. Then we have the correlation matrix down here, whereby, okay, the correlation matrix helps us to determine in the correlation matrix, so the EEG signals in that file specifically, we have the EEG signals on both sides. So here we're able to determine both the weak and the positive correlation and the negative correlation. Now, the positive correlations are represented in red, and the negative correlations are represented in blue. While the light blue and the light red, those are the weak correlations. So here we have these ones which show a strong positive correlation. A strong positive correlation is represented in dark red, while a strong negative correlation is represented in dark blue. And then the light colors are for the weaker correlations. Then I proceed to talk about this is how the EEG signals appear. This is a graph showing the EEG signals from someone who's solving a mathematical problem. Yeah, we have the EEG signals on the y-axis, EEG channels, sorry, on the y-axis, and the different time, like measured maybe in an hour. This is in seconds. So from between 0 to 50 seconds, that's how the brain activity is. Between 50 to 100 seconds, we shall have the brain activity. So it displays the brain activity according to the seconds in between different EEG signals. EEG channels, sorry. Then we have the EEG signal amplitude distribution. It displays the strength of the signals. So it displays the strength of the different signals that we have. And on the y-axis, we have the frequency, the strength of the signal. And then we have the amplitude. So these EEG signals are measured in microvolts, and that's the amplitude. So we proceed to these other graphs where we have the time series counter and the timestamp. Yeah, whereby on the y-axis we have the amplitude and the time, and on the x-axis we have the time measured. Yeah, so the amplitude of the time series on the counter and the amplitude of the time series on the timestamp. Sorry. Then we have the EEG spectrogram. Okay, this is used to measure it's used to display the different signals according to different conditions. So here we have the power spectral density on the y-axis, and on the x-axis we have a frequency of those signals. So we have a color-coded scale, as you can see. So this shows this is 2.5 as you're moving from low to high. So the highest is yellow, as you can see here. That's the highest frequency, which is yellow. So it measures frequencies in different conditions. And the lowest is purple. Yeah. Then we proceed to the violin plot. So the violin plot almost does the same work as the box plot, but the violin plot this time is a combination of a box plot and a KDE. It's like an advancement of a box plot. Yeah, and that's how it appears. It also shows distribution of data. Then we have the burn power graph. So the burn power, as we know, the delta shows states of sleeping, or it mainly shows it's the slowest. It has the slowest waves, and it shows a sleeping state or maybe the brain activity in infants. Then theta shows drowsiness. It also shows sleeping states. Then we have alpha. This displays a more active state, like when someone is awake and relaxed. And then we have the beta, which also shows an activity state. So the beta is used maybe when someone is working out a complex mathematical problem. That's when we use the beta waves. And then the gamma waves are for high cognitive activity. Like when someone is trying to remember something or to perceive something, that's when we use the gamma waves. So they are plotted in terms of the power of the wave on the y-axis, and the timestamps, the channels, the EEG channels. Yeah, there's different variations. So I proceed to the next. Okay, this is what we got from our models. We used 10 models, which is a random forest, the XGBoost, knowledge distillation and contrastive learning model, the bidirectional LSTM model, the decision tree, the SVM, naive Bayes model, the EEG net, and the contrastive learning model. So this is the different output that we got from each of the models, the accuracy, the precision, the recall, and the F1 score. But we chose to go with contrastive learning because it was what suited our project most. So we go on to the next. This shows the different the confusion matrices of most of our models. So for the random forest, okay, our confusion matrix basically shows the different classification of the data, whereby here we are seeing the complex mathematical problem solving, these are the classes that we have in our, they're the classes that we have in our data set. So it basically classifies the data. That's what a confusion matrix does. So we have the confusion matrix of a random forest. We have the feature distribution for SVM models. So it's selected like different features to be used for the model. And this helps improve the robustness and accuracy in that model. Yeah, so you can see that it displays feature, the feature value, and the frequency of the value in that feature. Then this is a confusion matrix for the decision tree. Then we have, this is for the random forest. It displays this graph down here for precision recall. It shows the different evaluation matrices for the random forest. Then we have the student models confusion matrix. This is from the knowledge distillation model. Yeah, we're able to pick out the student model and use that confusion matrix. And we have the EEG naive Bayes confusion matrix. These are the different matrices of our other models, whereby this one, this is for XT boost. Then the optimized contrastive learning, this is for the EEG net, though it's not labeled, sorry, but that's for the EEG net. Then the bidirectional is LSTM model. So in conclusion, this study introduced a robust framework for EEG-based mental stress detection using reinforced contrastive and non-contrastive knowledge distillation, enhancing the classification performance, the accuracy, and the generalization. So this project basically enables improved stress detection through classifying the through classifying in different evaluation matrices like performance metrics like high accuracy, precision, recall, so that we are able to tell the performance of the model. And it also enables us to handle small data sets and missing labels while maintaining consistent feature extraction. Then we have real-time deployment of the model using the Flask API, MLflow, and Grafana. This ensures scalability in healthcare or in different places, school, work, very many fields. Then the different limitations that we got in this project, our data set was in EDF format, which was a bit complex to deal with because you have to first install certain things to help you read this data. And it's also not so easy to read. It's not easy to understand. Yeah, that's why we needed libraries like MNE. But then we were able to develop automated preprocessing tools that helped us to overcome this. Then we have small and non-diverse data that limits generalization. So the different brain activity is measured in different ways, of which even the slightest brain activity is measured. And this is not, okay, it's not easily, it's very small. It can't help the model to maybe determine the state. So we're able to use data augmentation to make it clearer to the model, and transfer learning. Yeah, so this helped like to improve the performance of the model since the data set had very small, some waves are small, and sometimes it doesn't even have values. They are missing values. There are times when we don't have brain activity showing in our data set. So the missing values, which affected reliability, the model couldn't easily tell, and it was causing errors. yeah, it made it a bit difficult. But yeah, we applied robust imputation and domain adaptation. So our model was able to adapt to those missing values. And maybe when it lands on a missing value, it's able to skip it without causing an error. Then we have deep learning and overfitting. Deep learning overfitting that is caused by small data sets. So yeah, the model is not able to get enough, it's not able to learn from the data set, maybe due to its size, which leads to overfitting. And this doesn't, it's not accurate. If it overfits, then it's just memorizing, it's not learning anything. Yeah, but we're able to use regularization and ensemble learning to deal with this. Then the steps that we took, we expanded the data set by collecting diverse EEG data for better generalization. We're able to like we're able to expand the data set in a way so that the model is able to read from that data. Then hybrid models, combining different techniques to help the model. And then self-supervised learning, the model is able to learn on its own without maybe learning from the data set, labeled data set and all that. So it enhances the feature extraction for unseen data. Then we have Edge AI optimization, whereby we developed lightweight models for real-time stress detection, because we want to detect the stress in real time using maybe wearable sensors. And then, however, we're able to improve model interpretability using explainable AI, and we enhanced the real-time deployment so that we can be able to detect stress in real time. Yeah, we're able to integrate multimodal data, whereby we combine EEG with physiological signals like HRV and GSR for better accuracy to prevent those different errors. Yeah, ethical and privacy measures, since we don't want to expose people's data, people's brain activity to unauthorized personnel. And in conclusion, we'd like to express our sincere gratitude to our lecturer, Mr. Galim Kumabi, for his guidance and encouragement throughout this research. Yes, we also extend our appreciation to Makerere University for providing the necessary resources that we needed to conduct this research. And special thanks to our colleagues, friends, and family for their continuous motivation and support. We also acknowledge the contributors to this research, the different contributors, the people who helped us in this research work. Thank you and have a nice day.